Hello everyone. I am Haruki Okada, software engineer. I work as a member of Line Z-Part team, which develops company-wide Apache Kafka platform. And I am also a Decaton maintainer. I will talk about Decaton today. Now, these days, for web application development, background task processing is crucial for quick response time to enable better UX and workload separation for stability, and also failure isolation. This includes, for example, push notification, calling webhooks, and updating the search indexing. Also, in service development at Line, background task processing is often utilized. It's quite challenging to process massive background tasks without spoiling task processing stability at maximum resource utilization efficiency. Decaton is Kafka consumer framework that our team developed. This is aimed to implement reliable task processing efficiently. Decaton is battle-tested in Line service development for years. High performance is the most important feature Decaton provides. Today, I will talk about why we developed Decaton, not existing Kafka consumer framework, and what is it like to do the task processing using Decaton. And lastly, our engineering efforts to maintain high-performance software like this. I'm sure that many of you might know this, but Apache Kafka is a middleware for streaming processing. Apache Kafka is one of the most popular middleware in Line. Over 90 services use company-wide Kafka platform that our team developed and operate. Typical use case of Kafka at Line is background task processing, including external I/O. As you can see in this diagram, Web API produces tasks to Kafka, and task processor receives them and processes them in background. Kafka is a middleware optimized for data streaming. In comparison to API server executing external I/O directly to the storage, basically the Kafka produces tasks to Kafka, and this can be done reliably and efficiently. The background task processing using Kafka at Line is shown here as an example. When Line user updates profile, friends will receive notifications. Here, the API server, instead of sending notification at the time of the update, it sends a task processing to the background, and task processor sends the notification asynchronously. At Line, we often have I/O-intensive background task processing, such as database access and web API calls. Also, at Line, the task processing traffic is large scale. Most high traffic use case actually has over 1 million tasks per sec. Also, the reliability of task processing is crucial. Huge amount of traffic needs to be handled, and all tasks need to be processed as at least once delivery. Now, why did we develop Decaton, not using the existing consumer framework? In order to talk about that, I'd like to first of all introduce the basic architecture of Kafka that you might be familiar with. In Kafka, The similar messages are categorized into units called topic. For example, at the time of the profile update, this is one topic, and other example is the impression log of ads. One topic is sharded into multiple partitions. Messages produced by producer are partitioned based on message keys. In the partition, the sequential number or so-called offset is allocated. Each partition is assigned to one of the consumer in the consumer group, and consumer receives offsets from partition and process them starting with the lowest number. By doing this, each partition behaves as a message queue. Consumer commits the processed offset to Kafka, and when consumer restarts or crashes, it resumes processing from the committed offset. Each consumer gets assignment either 0 or multiple partitions, but one partition is processed by one consumer. So if the number of the consumer instance is higher than the number of the partition, the redundant consumers become idle. Therefore, in Kafka, maximum consumer concurrency is limited by the number of partitions. Now let's look at the basic consumer implementation example. Consumer loops and continuously calls API called poll, thus reads messages from assigned partitions, then processes read messages by poll. After processing is completed, offset is committed. This series of processing, or infinite loop, is the basic behavior of Kafka consumer. So thread running infinite loop is called consumer thread. As I said, Kafka partition is characterized as queues, therefore guarantees the sequential processing. Consume is done in the order of produce in order to keep the semantics as queue. Consumer basically process messages sequentially. Other consumer frameworks such as Kafka Streams and Spring Kafka are also based on this processing model. But synchronous processing like this could have an issue of throughput. In this type of synchronous model, the latency to process one message could limit the throughput per partition. For example, when I/O processing like Web API call is done, say that if there is a 10 millisecond latency, then this consumer will wait for the completion of I/O and processes only 100 tasks per sec per partition despite high availability of resources. So why not add more partitions so that we can increase the concurrency and to improve the throughput? But it is often difficult to precisely estimate the number of partitions needed when consumer is deployed. At the same time, adding partitions in Kafka is an administrative job requiring contacting cluster administrator. This could be a burden on both consumer developer and cluster administrator. Also, adding partitions has side effects such as breaking message ordering temporarily. Also, partitions are unit of consumer concurrency and at the same time unit of producer batches. Adding partitions generate the smaller batches. Number of produce requests increases, requiring more system resources of brokers. Also, it affects number of open file descriptors and memory mapped files. If you attended the Kafka-related session on the Dev Day 2 years ago, you might know this, but our team's operation policy is single multi-tenant shared Kafka cluster. Here, the Kafka cluster is a shared resources for multiple services. So consuming system resources of unnecessary broker is not desirable. So now we know in synchronous task processing model, we have an issue of throughput. So why not process tasks asynchronously? For example, separate thread pool to process tasks can be generated, and instead of synchronous processing, we can submit this to executor service and then commit the offset. With this method, the consumer throughput can be improved significantly. But with this simple asynchronous model, reliability of message delivery could be sacrificed. For example, messages offset 1 to 5 are fetched. Messages are submitted to executor service and then commits offset. Since this is asynchronous, order or process are not guaranteed. So here offset 1, 2, and 5 are completed, but not 3 and 4, and unluckily say that consumer crashes at this point. Other instance takes over from offset 5. So in this example, offset 3 and 4 processing would be lost. So, as you can see in this example of code, why not wait for the completion of asynchronously submitted tasks and then commit? Compared with the synchronous mode, throughput should be improved significantly, and there is no concern about lost messages. But with this method, when a part of tasks in preceding batch take time, all proceeding processes will be blocked. This could be an issue. So this is head of line blocking. The tail latency of task processing could directly affect the delivery latency of all proceeding processes. Ideally, in this example, all preceding tasks should be done, so offset 3 is committed, and continuous processing will continue without waiting for the 4 to be completed. In Decaton, the highest offset that all preceding offsets are already processed is called Watermark. In other words, what we need here is a mechanism to track Watermark under the condition that the multiple threads are executed in arbitrary order. So how can we realize this? As I said, the watermark is the highest offset that all preceding offsets are already processed. We can calculate the watermark by iterating over completed offsets in ascending order and checking corresponding fetched offset. In order to do this, priority queue can be utilized. Our initial approach was to use priority queue. First, consumer thread registers fetched offsets as pending offset queue, then submits tasks to processor threads. Processor thread put completed offsets to priority queue and checks pending offset and completed offset from the beginning, and when they match, watermark proceeds.
We have applied this to a task processing with 1 million traffic per second and tested it in a production environment. This task involves writing to HBase. As a result, we found that, contrary to our intuition, the watermark tracking mechanism has become more of a bottleneck than the writing to HBase itself. This slide shows an asynchronous profiler in the reproduction environment, but a lot of time is spent waiting for the lock. The approach with priority queue unfortunately required lock in multiple places. First, the priority queue stores the already processed offsets and enqueues them for multiple processor threads concurrently. Lock is therefore required to protect this. Also, to prevent the queue from growing indefinitely, the watermark is matched against each offset. The unwanted offset below the watermarks are removed from the queue, which again requires the lock. The problem is that the shared object, priority queue, is mutated concurrently from multiple processor threads. From this, we can think of an idea. Is it possible for each processor thread to mutate only on its own offset state and track the watermark in a non-exclusionary way? Based on this idea, we improved it to a lock-free form with a ring buffer. This approach represents the processing status of the offset as an element of the ring buffer. First, the consumer thread resolves the retrieved offset to the ring buffer index and initializes the state of the offset. At the same time, it sets the watermarker pointer to the initial position. Next, the consumer thread throws the task to each processor thread, which will mark the buffer's element corresponding to its offset as complete when the process is complete. Then in the consumer thread, we proceed with the watermark as long as it is completed. This way, each processor thread will mutate only for the offset it has processed, which is a unique reference in the ring buffer and therefore does not need a lock. As a result, lock contention, a problem with the initial approach, has been eliminated, and watermark tracking is now a nearly negligible part of the overall process. In this way, we have an optimized watermark tracking mechanism. This mechanism is the core of Decaton's high-performance task processing. Now that we've talked about this topic, you may be wondering what the queuing nature of the Kafka partition or process ordering guarantees would be. Decaton assigns the message retrieved in the consumer thread to the queue in each processor thread based on its key. This process allows Decaton to guarantee a per-key processing order with slightly relaxed ordering guarantees per partition. In Kafka, messages are partitioned by key, so for most use cases that require a per-partition order, this per-key guarantee works well enough. Here's a summary of Decaton's processing model. In Decaton, unlike many consumer frameworks, a single partition can be processed by multiple threads. In this case, the order of processing task is guaranteed on a per-key basis. It also preserves at least one semantics while performing multi-thread processing. And since there is no task waiting by batching, the task delivery latency is also stable. This slide shows a benchmark comparison with Kafka streams and Spring Kafka, which are sequential processing models per partition. For test cases with high latency per task, Decaton shows a significant improvement in throughput by increasing the concurrency per partition. Now let's see what task processing looks like with Decaton, with some actual codes. We will use the example of line users profile update notifications from the beginning. The steps required are straightforward. First, define the protocol. Then implement the task producer, and then implement the task processor. First, define the protocol. Since it is a profile update notification, it will contain things like the user ID and a friend IDs list to be notified. By the way, we use protocol buffers here, but there is no restriction on the format of the task in Decaton. Next is implementation of the task producer. Decaton provides a class called Decaton Client that wraps Kafka Producer, which takes the role of task producer. We then implement the task processor. On the task processor side, we first create an implementation class of the Decaton processor interface to describe the task processing content. Next, hand over the implemented processor to the subscription builder and start the Decaton subscription. That's all. As you can see, it is very simple to use. Decaton has also implemented many features commonly needed in task processing based on the needs of actual line services, while focusing on high-performance task processing. Today, we are going to introduce two of them. First is rate limiting. For example, you may want to protect a downstream database DB or web API that is being accessed from the task processor from a large number of sudden traffic tasks. Since Kafka is a persistent streamlining middleware, you can use Kafka as a buffer to smooth the traffic by throttling the processing pace on the Decaton side. Setting such rate limits is very easy in Decaton. All you need to do is add a few code lines to set the rate limit in this way. By the way, a rate limiting can be changed dynamically and set statically, as shown in this code example. Rate limiting allows the process to continue at a constant speed, regardless of the number of tasks generated. Another feature to introduce is retry queuing. In some cases, such as when the downstream DB access from the task processor becomes temporarily overloaded, access may intermittently fail. If you retry the process until you succeed, you may block the subsequent task processing, although the impact is mitigated thanks to Decaton's processing model. Also, it is, of course, undesirable to throw away a failed task. For these cases, Decaton has a built-in retry queuing feature. With this, when the access to storage from the task processor fails, instead of retrying the process, it will produce a retry task to Kafka. The reattempted task is processed by the task processor again after a certain amount of backoff. To do this, first, prepare a topic for the retry task. Then add the code to be tried as needed within the processor. All that's left is to add a line to the subscription builder to enable the retry feature. These features have also helped Decaton to be used by several and many line services. These are just a few of the services, but we are sure you use some of them often as well. The Line Engineering blog has an article about a case study in smart channels, an example of the system's unique use that I won't talk about today, so please look at it if you're interested. By the way, an interesting article about experimental support for WebAssembly in Decaton was recently posted on the engineering blog. Currently, Decaton only targets the JVM-based language. Still, if we can realize this, it would allow us to write the Decaton processor in any programming language compiled into WebAssembly, allowing us to utilize Decaton for more use cases. You might also enjoy this exciting article because it goes into some detail about the WebAssembly system interface, so please look at it if you like. Let's talk about our efforts to keep Decaton at high performance in the end. Performance is affected by a variety of factors. For example, adding or refactoring features, changing the default configuration values, and upgrading dependency libraries, such as Kafka clients, can also impact. We are looking for an integration benchmarking environment that measures performance from end to end, from producing the task to the actual completion of the process, rather than micro benchmarks for individual components. It is also essential to get a profile to identify the bottleneck at this time accurately. It is also necessary to measure the performance of each code change or Git commit so that we can identify which factors have affected the performance. To this end, we have developed this integrated benchmarking framework. First, the benchmarking process launches an embedded Kafka cluster. Next, we fork the benchmark Decaton processor application as a separate JVM process. The processor notifies via RMI that the initialization is complete, and upon receiving the communication, the benchmarker starts to produce the task simultaneously as launching the profile. Once communication is received via RMI that all tasks have been processed, we end the benchmark. We conduct this integration benchmarking for every code change as part of CI and store the benchmark results along with the profile. We also visualize the benchmark results to allow confirmation of the performance trends on the web UI so that problems can be detected. The mechanism looks like this. First, an integration benchmark runs in the CI server, triggered by a code change in the Decaton repository. We commit the result with the profile to the HBase branch to make it easier to go back to the profile in any given commit. Performance trends are then visualized using GitHub pages. This performance dashboard is also available to everyone from a web browser. Please open it if you wish. In summary, Decaton is a Kafka consumer framework that has been widely used and improved in the actual development of line services and is best suited for I/O-intensive workloads. We have also made significant optimization concerning offsetting commits to achieve high performance. And to maintain performance, we continually benchmark as part of CI. By the way, Decaton has recently become open source, so we invite you to try it out and give us your feedback. That's all for this session. Thank you for your attention.